Okay, welcome back to Unit 1 notes, and this is a combination of objectives 2 and 3 in Unit 1 Okay, so now we're going to build off of what we were doing in that first objective. The first objective we were doing just the parent functions, and now we're doing the more generalized functions. So really this is the more important lesson of the two. It's just we build off of that foundation from Unit 1. So let's go ahead and start with the lines. Okay, now lines, there is y equals mx plus b. I mean, obviously that's something that we do want to keep in mind. But really a nice form to have in our back pocket is known as point-slope form. Okay, point-slope form, where it's essentially that the parent function, the y equals mx, and we put a point in there. The point is x1 comma y1, and then you can see the slope. So if you take away the x1 and the y1, you can still see it's the y equals mx equation. Okay, could also be written, I mean, we can move the y1 to the other side. It becomes a plus y1 over there, and the x1, y1 can be replaced with an h and k as well. Okay, let's go ahead and try this now. Okay, so problem number 1, slope is negative 3/2. Okay. And the point, okay, now when it's in the parentheses like this, you can either say it's kind of opposite what the number looks like, or what would I plug in for x to make it 0 in there? -2. So -2. Now the 1 is over here on the other side. It's all by itself. It's not with the y, so it's telling you exactly what it is. It's a positive 1. Remember, the other way we could have it, we could move it over. So if we did that, we would have y equals, excuse me, I forgot I was moving it over. So y -1 equals the slope -3/2 times x plus 2. And if you have it in that form, it's like there's parentheses around it. Okay, now what would I plug in for y to make it 0 in there? Positive 1. So, yes, -2, comma 1, and -3/2. Okay, now a slope is nice, but you always have to lock things in with a point first. So the point is -2, 1. And then the slope is -3/2, which I was talking about yesterday. One of them's negative, one's positive, so I could do down 3 over 2. And I could do it again, down 3 over 2. Another way I could do it, I could also do it up 3 and then back 2. So up 3, back 2. And so now it looks like it's forming a line. So make sure you're drawing it straight. Okay, and we're doing domains and ranges, and we're going to keep on practicing, particularly with interval notation. So domain, left and right, goes left and right forever, so all reals. And the range goes up and down forever, so also all reals. Okay, now lines, if it's any kind of line where the slope is anything except 0, the domain and the range are going to always be all reals, provided it's a function. If the slope is 0, then the range is not all reals. Okay, well, let's pick up speed here now on number 2. So number 2, our point is 1, comma -2, and our slope is 1/3. Okay, so 1, -2. And the slope, 1, -2. And the slope is 1/3, so up 1 over 3. I go off the graph paper as I go to the right, so let's go down 1 and left 3. And so we can see, I did not draw that very well. Okay, again, domain, all reals, range, all reals. Okay, moving on, parabolas. Okay, now, again, all we're doing is we're generalizing it, so the vertex, instead of being at 0, 0, is going to be at HK. So, and it's very similar to what we were just dealing with. Okay, you can still see the basic form, the y equals ax squared, but the vertex is at HK. If the a is positive, it's still opening up. If the a is negative, it's still opening down. Okay, so let's see. Okay, so number 3 here, our vertex is at, okay, it's in parentheses. What would I plug in for x to make it 0 in there? Positive 3. And the 1 is not in parentheses there. It's not grouped with the y, so it's just exactly the 1. Okay, the a is positive. I know it's opening up. Okay, so vertex always got to be exactly on. Now, you always need at least 2 other points that are very accurate. Now, if you do what we refer to as lattice points. Lattice points are integer points. Okay, so 3, 1 is a lattice point because 3, 1, it's both integers. Now, if I go 1 point to either side of the vertex, the a value tells me positive 2, so up 2. Now, remember, this is not a slope. It is a curve, so don't extend beyond doing that, but we can get a very quick and accurate enough sketch going on right there. Okay, domain. Does it go left and right forever? I know it's going up. It does go left and right forever. Yes. All reals. Range. Does it go up and down forever? Well, it goes up forever, but it doesn't go down forever. What's its lowest elevation? 1. Does it touch it? Yes. 1, and then it goes up forever. Okay. Number 4, okay, now this time the negative 2, it's over here with the y. We could move it over so it's a positive 2, or I could leave it like that and kind of just envision that there's parentheses right there. Okay, my vertex is negative 1, comma 2. Remember, it's always x, comma y. And my a value is negative 1/3, so my parabola is opening down. So negative 1, 2. And okay, now, if I go left and right, 1, if I go 1 point to either side, it says go down 1/3. Okay, now, those are not lattice points. So I need to try to plug something else in so that I can get some lattice points. Okay, so, now it's a times negative 1/3, so I want this to be 3 something when after I square it. Okay, so well, if I do an x of 2, 2 plus 1 is 3, 3 squared is 9, times negative 1/3 is negative 3. If I do a negative 4 for x, negative 4 plus 1 is negative 3 squared is 9, times negative 1/3 is negative 3. So 2, negative 3, 2, negative 3. And negative 4, negative 3. And we can okay, so my domain, it does go left and right forever, so all reals. My range doesn't go up forever. In fact, my highest elevation is 2. and it touches the 2. My lowest elevation, it goes down forever, so that's coming from negative infinity. So negative infinity to my highest elevation of 2, and it touches the 2. Okay, linear absolute value functions. Very similar to parabola. We've got f of x or y equals a times x minus h plus k. And the k could be brought over like any of the others. Okay. Okay, so number 5. Our vertex is -4. Absolute value is sort of like parentheses here. Well, what I plug in for x to make it 0 in there, so -4. And then if I plug that in, I get 0 minus 1, so y is -1. So -4, -1, there's my vertex. And then my slope, remember this is linear absolute value. My slope, I've got down to right 3, and I've got down to left 3. And I know that goes off the graph a little bit, but sometimes you got to do that. Okay, domain goes left and right forever, doesn't miss any points in the middle. The range doesn't go up forever. The highest elevation is -1, comes from negative infinity to -1. Okay, exponential functions. Now remember I told you that the a value out in front is just going to be a 1. So really y equals b to the x minus h power plus k. Okay. Now again, if b is greater than 1, it's this basic shape. If b is between 0 and 1, and it's this basic shape where it's coming from high and going low. Okay, now these exponential functions are maybe the trickiest because they don't go through the origin normally. They typically go through the point 0, 1 unless you shift them. I think the safest way with these is just to get at least 2 points, if not 3 points. We can do just 2 points as long as we realize that, remember that there's a horizontal asymptote for the exponential functions. I didn't mention that yesterday, sorry, I apologize. But there is a horizontal asymptote, which is normally elevation 0 unless we shift it up or down. So, for example, number 6. The left-right shift will be up here in the exponent with the x's, and the vertical shift will be over here on the side. Because, in other words, we could actually even write this as your generalized function, y minus k equals b to the x minus h power. That would be the same thing. And if it was like that, then you'd put parentheses around the y minus k, or at least think of it that way. So on this one, we've shifted down 4. So normally at elevation 0, shift down 4. 1, 2, 3, 4. So there's my horizontal asymptote. So that gives me something. X, Y. Okay. So think of what would you plug in for x to make it a 0 exponent up there? Well, 2. If I get a 0 exponent, it would be a 2. So 2 minus 2 is 0. 3 to the 0 is 1. Minus 4 is -3. So 2, -3. There's a point. What would make it a first power? Well, a 3. Okay, so if I plug in a 3, I get 3 to the first, which is 3, minus 4, which is -1. So 3, -1. And so with the horizontal asymptote and those 2 points, I should be able to make a decent sketch of what's going on. Okay, my domain, it does go left and right forever. My range, it almost gets down to elevation -4, but it never quite touches it, and then it goes up forever. Okay. Number 7. It's y minus 3 over here. What would I plug in for y to make it 0 in there? Positive 3. Okay, so horizontal asymptote up at positive 3. Okay. What would I plug in for x to make it 0 up there in the exponent? -1. Okay. -1. So if I plug in a -1, I get 2 to the 0, which is 1. Okay. 2 to the 0, 1 plus 3 is 4. So 1, 4. And let's do a first power. So what would I plug in to get a first power right there? A 2. So I get 2 to the first. Sorry, not a 2. Not a 2. A 0. Which points out that I plotted the wrong point earlier. Okay, -1, 4. Let's try to do that correctly. -1, 4. -1, 4. And then 0, comma 5. And there's our sketch. Okay, domain goes left and right forever, so all reals. And the range, elevation 3 doesn't quite touch it, and then it goes up forever. Okay, we're going to write some equations of graphs, much like we did yesterday, only the ones yesterday were pretty much just parent functions. So for example, number 8 here, linear absolute value. So I'm thinking about y equals a absolute x minus h plus k. Well, what's my vertex? My vertex is 1, -3. Okay, so y equals a absolute x minus 1 minus 3. Double check, make sure that gets you the vertex you want. It does. Okay, now when it's linear, you can probably just count, or you can plug in the point that's highlighted as well. Okay, so this point that's highlighted is -1, 1, so we could plug it in, or you could count. So for example, from the vertex, I'm going up 1, 2, 3, 4, and I'm going left and right 2. So 4 over 2, and it's opening up, so we know it's going to be positive. Really, it should be 2. Or you could actually plug in the points. If we plugged in the points, it would look like 1 for the y, x, y. 1 equals -1 minus 1. There's my a value. Minus 3. So I could add 3. 4 equals a absolute -2. Of course, what is absolute value of -2? And so a is 4 over 2, which is 2. Okay. Now, but like I said, when it's linear, you can usually just kind of count it, and you don't have to do all the calculations. Now, on the other hand, when it is a curve, make sure you are plugging in the points. Okay, now, this one, number 9, is a curve. X minus h quantity squared plus k. And we can see the vertex. The vertex is negative 1, 2, 3, 4, up 1, 2, 3, 4, 5. So my vertex is negative 4, 5. So we could already plug that in. Y equals A times x minus a negative 4, so x plus 4. Don't forget the squared. If you forget the squared, it's not a parabola. Plus 5. Double check, make sure that that gets you the vertex you want. Negative 4, 5, yep, that does. Okay, now, don't try to just count it with parabolas. You got to plug in the points. So this point is negative 1, 2, x, and y. So if we plug those in, 2 equals a times negative 1 plus 4, quantity squared, plus 5. Solve for the a. So I could subtract 5, I get negative 3 equals a times, okay, I get 3, negative 1 plus 4, 3 squared, 9. And so negative 3/9 is a, reduce. We always reduce fractions, so negative 1/3. Okay, finally our last one here. We look at, again, it's a curve. Now, the horizontal asymptote is negative 1. It's at elevation 0 unless we shift up or down. It's shifted down because it's the horizontal asymptote's at negative 1. So I'll do that right now. Now, if it hasn't shifted, the exponential function will always go through 0, 1. Okay, and the 0, 1 is always exactly 1 above the horizontal asymptote. So negative 1, 0, that point is exactly 1 above the horizontal asymptote, and so compared to 0, 1, didn't it shift to the left 1 and down 1? We already got the down 1. The left 1 would be x plus 1. Okay, so that gets me a shift left 1 and down 1. Okay, so all we got to do now is figure out what the b is. And with the way we figure out what the b is, we're going to use the other point. Don't use the one that is normally the 0, 1 that might have gotten shifted. If you do, it'll be true, but it won't tell you anything. You'll end up getting like 0 equals 0. Use the other points. So there's x and y, plug them in. So 26 equals b to the x, which is 2, plus 1, minus 1. Okay, I'm going to add 1 to the other side. 27 equals b to the third. Okay, so some number to the third is 27. Well, 3 to the third is 27. Okay, and so b is 3. So y equals 3 to the x plus 1 minus 1. Okay, coming down the home stretch here. And we've got combining functions. So it could be adding, subtracting, multiplying. Well, not really. No, we're not. Sorry, we're not doing multiplying or dividing yet, but it could be. There's also something known as composition of functions, and it looks like what we're doing here on 11 and 13. Okay, so composition of functions looks like the g of f of x, or on 13 f of g of x. So it's like you got a function inside of a function. Okay, so if f of x is x plus 4, and g of x is x squared, find this new function, which is g of f of x. Okay, well, if we just kind of go through and do exactly what it tells us to do, h of x is equal to g of whatever f of x is. Well, what's f of x? Well, it tells us right here, x plus 4. Okay, so that's the first step. Now I just got to do g of whatever we're plugging in. Now, the function g says whatever you input, you're going to square it. So whatever I input, I'm going to square it. What am I inputting? Well, I'm inputting x plus 4. So that's what h of x is, what g of f of x is. It's x plus 4 quantity squared. Okay, and okay, so that's a parabola, a quadratic. My vertex is at -4, 0, because if I plug in a -4, I get y equals 0, -4, 0. In front is a positive, so I know it's opening up. In fact, it's a positive 1, so -4, 0. If I went 1 point to either side, I would go up 1. Okay, there's my new function. Okay, the number 12. If f of x is x squared plus x minus 2 and g of x is x squared minus 2x, then find the new function, which is f minus g. So, okay, let's just do what it tells us to do. So h of x is f, what's f? X squared plus x minus 2 minus g, which is x squared minus 2x, x squared minus 2x. And so if I distribute the negative and combine like terms, see how the x squareds are going to eliminate each other? And I get x minus a -2x, so x plus 2x, which is 3x and minus 2. Oh, it's a line, and it's in y equals mx plus b form. So my y-intercept is 0, -2. My slope is 3, so 0, -2. My slope is 3, so up 3 over 1, up 3 over 1. Okay. Number 13, if f of x is 3 minus absolute value of x and g of x is x minus 2, find the new function, which is f of g of x. Okay, so h of x is f of g of x, and g of x is x minus 2. Okay, so what do I do with the function f? My function f says whatever I input, I'm going to do 3 minus the absolute value. So h of x is 3 minus whatever I'm inputting. What am I inputting? X minus 2. Okay, so that's h of x. Now it's a linear absolute value function, so maybe it looks a little bit better to you if you do it like this. We don't have to rearrange it. The 3 is positive. My vertex is 2, 3, and it's opening down. Okay, so 2, 3, and -1, so down 1, right 1, down 1, other side 1. Okay, that's combining functions. Okay, last two problems. Graph and label f and g on the same coordinate axes. Okay, okay, so 14, my function f, I've got it's quadratic, vertex is 3, 2, the a value is positive 1/2, so if I went left and right 1, I would go up 1/2. If I If I went, let's see, I want something that would divide evenly by 2. So if I went, to the right 2, so if I went to 5, okay, so if x equals 5, 5 minus 3 is 2, squared is 4, half of that is 2. Oh, I forgot the plus 2. If I went to 1, 1 minus 3 is negative 2, squared is 4, half of that is 2, plus 2 is 4. So 5, 4, and 1, 4. Graph and label, so F. Okay, my function G, notice it also has the coefficient of 1/2. Of course, it's negative, so it's opening down, but my vertex is -1, -3, so -1, -3. And so since it's the 1/2, you know how we did all that, it'll be the same. So if I go left and right 1, it'll be down 1/2. And if I went left and right 2, and I went up 2, so this one actually goes down 2 though when I do that. And graph and label. So there's F and G. Okay, so now describe the translation from F to G. Okay. Well, let's go from vertex to vertex. So F to G. So from F to G, looks like we're going left and down. How much are we going left? 1, 2, 3, 4. So left 4. And down how much? 1, 2, 3, 4, 5. Down 5. And then it also reflected. Or flipped, kind of. Reflected over the x-axis, but let's say flipped here instead. Let's say flipped. Okay, last problem, and this is the only set of notes here for today. So f of x, f of x is an exponential function. It shifted down 1. I'd like a 0 exponent, so I'd plug in a -2. If I plug in a -2, I get 1 minus 1, which is 0. -2, 0. I'd like a positive 1 exponent, so if I plug in a -1, I get 3 to the first, minus 1, 2. Okay, using the horizontal asymptote and those 2 points, there's my sketch. Okay, sketching G. Okay, plus 2, so it shifted up 2. And I would like a 0 exponent, so if I plug in a 4, I get 3 to the 0 plus 2. Notice how that first point is exactly 1 above the horizontal asymptote. I'd like a first power, so I'll plug in a 5. And so 3 to the first then, plus 2. Sorry, I didn't plot that in the right place, did I? Two, 4, 5. Okay, there. Because these two graphs are essentially the same graph, it's just that they are translated. So from F to G, well, focus in on the point that would be like the 0, 1 comma point. So from F to G, from -2, 0 to 4, 3. So from -2 to 4 is right 6. And from 0 to 3 is up 3. So just double check, does that make sense? From F to G, right 6 and up 3. Yep, that looks like it makes sense. Okay, you have all the tools you need now to be able to do both worksheets. Worksheets 2 and 3 in Unit 1 packet.